Okay, it's the beginning of week 6. So today is Monday, May 4th, and we're going to continue talking about magnetism and magnetic fields. So a lot of forces you can see. So if you punch a bag, you are physically seeing the punch. If you kick a car, then it's going to kick back at you, so you can see the forces there. But then there's some forces you can't see. We mentioned before gravity being a good example of that. And electromagnetism is another example of this. So as you can see, even though the magnet is not physically touching the beads, it is still able to attract it. And over here, even though the magnets are not touching, they're still able to repel. So it's because of these magnetic fields that are created. On page 83, we're going to take notes on this. So this is PS2-5 about magnetic fields. And in magnetic fields, you're able to exert forces even though things are not touching. In other words, magnetic fields, they are created at a distance even when not in contact. So if you remember Coulomb's law from last week, the bigger the distance between the two objects, the smaller the resulting force. So if you have two magnets across the room from each other, they're probably not going to exert too much force in each other. But if you put them nice and close to each other, then they get stronger and stronger. The force between them gets stronger and stronger. Here are some more examples of magnetic fields and the uses of them. So we have a metal detector. As you can see, this person is at the beach. He's going to go around and look for anything that's metallic. And what's happening is this metal detector doesn't have to touch the metal thing. It can just sense the magnetic field around the metallic object and can pick it up. When you go to the airport, they scan you for weapons or things that they don't want you to have. So the hand scanner will check for magnetic fields, and then these walk-through scanners will do the same thing and stuff like that. Let me show you a quick video of a person who bought this contraption to show off his really fancy sneakers.
I'm nervous. This thing is so powerful. I'm gonna go to 450. Okay. Now it's not touching anything. And it's spinning. Never mind walking on water. We're levitating too now. Oh man, that is strange. It's strange. It's a good time though.
Okay, so as you can see, like that contraption allowed him to levitate his shoes even though the shoe was not touching. So the magnet and the electromagnetic, when he turns it on, it becomes electromagnetic, allows the shoe to float. Now, if you built this on a bigger scale, you can create trains. So in Japan, they have these things called maglev trains, and what they do is they use magnets, and it allows these magnets to float the entire train, and then by alternating the north and south, it actually pulls the train along with it, and it goes super fast. There's very little friction. The downside is it does cost a lot of money, so I have a quick video to show you about that. All right, have a good day. See you tomorrow.
What is a maglev train? The word maglev comes from the combination of magnet and levitation. Maglev trains take advantage of a physics principle that says two like magnetic poles will repel each other. For instance, the north pole of one magnet and the north pole of another magnet pointed at each other will push away from each other. But if we put a south magnetic pole and a north one together, they will attract. Maglev trains take advantage of both of these ideas, not only to provide levitation, but also propulsion. In order for the train to levitate, the two like poles are forced to repel each other like the magnets shown here. To provide propulsion, the train is outfitted with a north and south pole magnets along the sides. The track also has north and south pole magnets whose poles can be switched quickly. As the poles are switched, the train is attracted to and then repelled by the same magnet. The faster the poles switch, the faster the train goes. Now you may be asking yourself, why is all this necessary? We already have trains. Maglev trains offer one key advantage over typical rail and high-speed rail, and that is minimal resistance. Unlike other trains that must stay connected to the rail, maglev trains can float above the rail, only having to overcome air resistance. The only problem with maglev trains are that they are very expensive, costing between $50 and $200 million per mile. Compare that with a reported $82 million for high-speed rail and a meager $2.5 million for typical rail service.